Hello everybody, welcome to VTU EduSat program, a live web telecast of 15 CV32 strength of materials, which is common for both civil engineering branch as well as for mechanical engineering branch, and I will be dealing with module 2 on compound stresses, and the reference book for this is Ferdinand P. Beer and E. Russell Johnston, which is Mechanics of Materials, published by Tata McGraw-Hill, 3rd edition, SI units. And I am Dr. S.V. Venkatesh, working as a professor in the Department of Civil Engineering, PS University, earlier PS Institute of Technology, Bangalore. The syllabus as per the VTU, as per the university, Vishweshwara Technological University, is under module 2, that is compound stresses chapter, is Introduction, State of Stress at a point, General two-dimensional stress system, Principal stresses and principal planes. Then at the end it is Morse circle of stresses. Now we will start with the introduction. Earlier you looked from chapter 1, which is on simple stress and strain, where you have studied about tensile stress, which is because of the tensile force as indicated in the diagram here, this diagram. So the force is indicated as F, and there is force at the bottom also, which is a tensile force, and the stress developed in this is the normal stress, that is a tensile stress, which is given by the force divided by the cross sectional area. Then you have also studied about compressive force, which is because of the compressive stress, which is given in the second diagram, that is this diagram, where again the stress developed is force divided by the area. Then you have also studied about shearing stress, which is because of the shear force, which is given in this diagram, the third diagram, which is the force divided by the shear area, shear force divided by the shear area. Now you have studied about all this in the first chapter individually. What is the effect of these forces on the members when they are applied individually? Now in this chapter or in this module, you are going to study about what happens if these forces are applied onto a member in combination. Now let's see what is the state of stress at a point. Now if you take any point in a member which is subjected to different types of loadings, this is what you are going to see. Now at a point in a member, it could be subjected to a stress along the x-axis, which is denoted as sigma x. Now here I have taken it to be tensile stress. Then on this axis it could be subjected to sigma y, which is again a tensile stress. Then along the z-axis it is sigma z, which is also tensile in nature. Now along with this you will also have shear stresses, which is denoted as sigma xy here in this, which is parallel to the plane xy. Then it is also subjected to sigma xz, which is parallel to xz plane. Now similarly along this plane as well as in this plane, it is subjected to shearing stresses with the appropriate sign convention. Now that makes it the most general state of stress at any point may be represented by 6 components. Now the 6 components, as I have explained it as sigma x, sigma y and sigma z, they are the normal stresses, and tau xy, tau yz and tau zx the shearing stresses. Now it is to be noted that sigma xy is equal to sigma yx. Where is sigma xy? This is sigma xy, and sigma yx, sigma yx is here. This one is sigma yx. So this for shearing stress and this shearing stress, they have to be equal. Similarly others also, that is sigma yz should be equal to tau yz should be equal to tau zy, and tau zx should be equal to tau xz. Okay. Now what happens if this state of stress is rotated by an angle theta, which is indicated here? So if this is theta, similarly this would also be theta and this would also be theta. Now if it is rotated, then you get a new state of stress, which is sigma x dash, sigma y dash and sigma z dash, and correspondingly tau x dash y dash, tau y dash x dash and tau z dash x dash. So this is going to be the sixth state of stress, that when you rotate a member or a point when it is get rotated. Now let's see next what happens. Same state of stress is represented by a different set of components if the axes are rotated, which I have explained it just now. Now the general two-dimensional stress system. Now in case if we don't consider the stress acting along an axis, now in this case, which is called as a plane stress state, the plane stress is state of stress in which two faces of the cubic element are free of stresses. For the illustrated example, the state of stress is defined by sigma x, sigma y and tau xy, and sigma z, sigma and tau x zx and tau zy are considered to be equal to 0 as indicated in this diagram. We are considering sigma x, sigma y and tau yx and tau xy are considered. So that is nothing but plane stress. It is defined as plane stress, which is the general two-dimensional stress system. Now this can also be represented by this, where you take only one plane and there are several forces acting, and you take a point in the plane here as represented in this diagram. This is going to be the state of stress that is going to be acting on any point. Now state of plane stress occurs in a thin plate as indicated here, subjected to forces acting in the mid plane of the plate as indicated in this diagram. Now state of plane stress also occurs on the free surface of a structural element or machine components, that is at any point of the surface not subjected to an external force. Now you can observe in this, the forces are subjected here F1 and F2 in this diagram, but if you take the surface of this at this point, this could be subjected to a plane stress where you have sigma x, sigma y and tau xy and tau yz. Now this is also represented in this diagram. The same whatever I have just now explained is represented here. All the three combinations are given here. General state of stress at a point is characterized by 6 independent normal and shear stress components, as I have explained: sigma x, sigma y, sigma z, tau xy, tau yz and tau zx, which is indicated in this diagram. Okay. Now from this you can take this where it is the plane stress which is acted upon by sigma x, sigma y, tau xy and tau xy on this plane. Okay. Now this is represented here when you rotate this diagram by 90 degrees along the y axis, that is this axis, you are going to get this, or along the x axis also you can rotate it, which would be like this, which is subjected to sigma x, sigma y and tau xy. Okay. These are the different way of representing the stress at a point. This is 3-dimensional and these two are the 2-dimensional stress elements. Okay. General plane stress at a point is represented by sigma x, sigma y and tau xy, which is indicated in this diagram, which act on 4 faces of the element. These are the 4 faces as indicated in this diagram. Now let's see, when we consider this general plane stress problem, how to determine the normal stress and the shearing stress on a plane which is inclined to the vertical by an angle theta. Now for this I would also like to use the blackboard here to obtain this normal stress on this axis. So let's see what happens here. So we are taking it's actually like this, the 4 elements. This is subjected to sigma x along this sigma x, and then this is sigma y. I am considering everything to be positive, that is this produces a tensile stress, this will also produce a tensile stress, then it is subjected to shearing stress here. This is tau xy. Please note that I am taking all this as positive, tau xy. And what is my intention? My intention is to find out what is the stress acting on this plane, okay, whatever is the normal stress. Now this plane is inclined at an angle of theta, so this is the normal stress. This is the positive axis of the normal stress which I am considering, which I am denoting at sigma n, and this would be the shearing stress which I am denoting as tau. Okay. Now, how do I get these values? Now, one thing that you should remember when you are looking at stresses and finding out the normal stresses is, the stress whatever is given, first we need to convert it into a force when we are resolving. We cannot directly resolve a given stress along any axis. First we need to convert the given stress into a force, and then only we will be able to find out or find out the component along different planes and add them, or take the sum of the algebraic sum. Okay. Now, let us take this element separately. I will write this element again, and let this area be A. Now, we are taking this to be the angle theta. So, if this is area A, this would be equal to A times cos theta. I am talking about the areas now, and here it would be A times sin theta. It is just simple trigonometric relationships that we all follow. So, if I want to take this stress system and find out what is the forces acting on these planes, so by considering this, I would get this as the forces that is going to be acting on these planes. Now, here this is subjected to sigma x as the stress. So, sigma x into the corresponding area will give me the force, that is A cos theta. Similarly, along this plane where I have taken it as sigma y, this into the corresponding area is A sin theta. Okay. Whereas, this normal stress which is acting on this plane is sigma n. So, corresponding area is A into A. This would be the force that is going to be acting. Then the shearing stress, if I take, this is tau into, again the area of this plane is A. So, it would be A. Now, we also have the shearing stresses acting on these planes, which should also be considered. So, we will get this as the shearing stresses, which is tau xy into the area of this is A, it is sin theta, whereas this one would be tau xy into A cos theta. Now, the stresses that was acting on this plane was same, but the forces that is going to be act, it will change depending upon this angle theta which we have taken. Now, that is what is indicated in this diagram. If you observe it carefully in this diagram, whatever I have written the last diagram on the board, that is what is indicated here. So, you have sigma x dash, in fact I have taken it as sigma n, whereas here it is sigma x dash. Okay. Let me denote this in the same way, sigma n, instead of sigma n it is sigma x dash, and whatever is given there is tau x dash y dash into A. That is what is indicated. Now, instead of taking area there in this diagram, it is taken as delta A, which indicates that it is a small area that we are referring to. Okay. So, the forces that is going to be acting here is sigma x delta A, I have written it as A cos theta, and tau xy delta A cos theta, which I have written it as tau xy A cos theta. Instead of delta, I have taken it as area there, that is it. So, this one would be tau xy A sin theta, and it is indicated as delta A sin theta, and sigma y delta A sin theta along this. Okay. Now, if I take all the forces that is going to be acting along this plane, that is x dash plane, okay, which is along this, let us sum up all the forces that is going to be acting along this, okay, which is given here as sigma f dash equals 0. In this, you can see all these forces are because of the sigma x that is acting, then sigma tau xy, that is this one, then sigma y delta A sin theta, and then tau xy delta A sin theta. So, these are the components that we are going to get. Now, in addition to this, the stress that is acting here, that is sigma x dash into A, will also come as the force that is acting. Now, this one would be positive, the force along this is positive, whereas this when I resolve it along this. So I would rather write it here as a separate diagram which you can understand it in a better way. So what we are trying to do is we are trying to find out all the forces that's going to be acting along this axis. This axis is nothing but the sigma x dash axis. So into the area is the force that's going to be acting. This is the first one. Next we have this force which we have indicated. When I resolve it, this angle would be same as this, which is theta. So if I resolve this, this would be sigma x a cos theta into this is the force, sigma x into a cos theta is the force. When I resolve this along this plane, I would get this as cos theta. That is what is represented here. Now the sense of this force would be opposite to that of this. So that's why a negative sign has come here in this equation. I hope you have understood this. Next, let's take the shearing stresses that's acting, which is along this. This is a shearing stress that is acting, which is tau xy a, again it is cos theta as I have indicated here. So this has to be resolved along this plane. Okay. So if I want to resolve it along this plane, this is the angle theta. So this force when I resolve it, I get it like this, which should be tau xy a cos theta. This is the force because of this. When I resolve this force along this, I get it to be sin theta, which is indicated here, because this one when I resolve it along this, this becomes into sin theta. So again when I resolve this, the sense is opposite to this. So that is why you are getting this to be a negative sign here. So now we have covered the forces that's going to be acting on this face. Let's look at next what are the forces acting on this face and then resolve that. Now similar to this, the forces that's acting on this face is sigma y into a sin theta. We have to resolve that along this axis. Okay. So that is along this axis. This angle is what is theta. So if I resolve this along this, I get this to be the force that's going to be acting here as sigma y into a sin theta. This is the force into the component. If I want it along this, it's going to be sin theta. Again the sense of this when I resolve it, it is going to be downwards opposite to this. That is what is indicated here as negative sign, sigma y delta a sin theta into sin theta. Next you take this one which is tau xy into a sin theta. I have to resolve it along this. Again when I take this and resolve it along this, I get the sense to be opposite to this. Again we will get it to be negative as indicated here in this. So it is tau xy delta a sin theta. When I resolve it, it comes cos theta. So this is the equation that we get when I resolve all these forces along this plane, which is the normal axis. Okay. Now these are the forces that we get. Okay. Next, now I want to find out what is tau x dash y dash. That is the point that we have. So now when I resolved it along this, we got the equation what I have just now explained. Now I am going to resolve the forces along this plane, okay, which is indicated in the diagram here. Now sigma f y dash equals 0, that is along this axis we are resolving. It is tau x dash y dash delta a, which is because of this force which is in the same plane, which has the same sense as that of y dash. So it is positive. Then if I resolve this sigma x a delta a cos theta, so I would resolve it in the opposite sense. Now you can see that we have resolved this along this axis. So we have got this. So when I resolve this along and normal to this, I will get the sense to be this, which is same as that of the sense of tau x dash y dash. So I get it to be positive. This when I resolve it, I get it to be positive, which is along with this. So that would be sigma x delta a cos theta into sin theta. Okay. Then the sigma xy delta A cos theta, this force I have to resolve it parallel to this. So when I resolve it, I get it to be acting opposite in the opposite sense as this. So I get it to be minus tau xy delta A cos theta into cos theta. Now similarly, the forces acting on this face, if I take this face, now this force, when I resolve it along this plane, okay, along this plane, I would get it the sense to be opposite to this, so that's why it is negative. Then the force is sigma y delta A sin theta, and when I resolve it, I get this is theta, so I get it to be cos theta. Similarly, if I want to resolve this along this plane, when I want to resolve this, I get this to be acting along the same sense as that of y dash, so it is positive tau xy delta A sin theta, and when I resolve it along this, I get to be sin theta. These are the algebraic sum of the forces which are acting along the normal axis, which is denoted as x dash in this diagram, and perpendicular to it, which is y dash. So if I resolve this by using the trigonometric relationships, I am going to get the equation which is appearing now on your screen. Now rewriting this, okay, the equations may be rewritten to yield sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Now it is better that I explain how you get this equation. That equation is obtained, okay, I think I will erase this and then explain that. Okay. So the equation that we have got here is sigma x dash into A or delta A minus sigma x A cos theta into cos theta, which we will get it as cos square theta, minus sigma y A sin square theta minus tau x dash y dash, sorry, tau xy A sin theta into cos theta minus tau xy cos A cos theta sin theta. Now this equation is what we have got from the from whatever I have explained earlier. So to transfer this and get the equation for the normal axis, cos theta, we know what is cos square theta. I can write cos square theta as 1 plus cos 2 theta by 2, and then sin square theta as 1 minus cos 2 theta by 2, as well 2 cos theta sin theta as sin 2 theta. This is the formula which you will get it from trigonometry. So substituting this, we would get, when I substitute this here, we would get this. I will transfer this on the other side, and you can see that you have the area in all the terms, so I can cancel those terms. So I get sigma x dash equals this. I am transferring on the other side of the equation because this entire equation should be equal to 0. So we get this as sigma x into cos square theta. I am substituting this, so it is 1 plus cos 2 theta by 2. Then we have this again on the other side of the equation, so it becomes plus sigma y sin square theta will become 1 minus cos 2 theta by 2, and then this minus, this is also minus, when it goes on the other side it becomes plus. So these two I can add, so I get this to be 2 sin theta, 1 sin theta cos theta sin theta, so I can add, this becomes 2 cos theta sin theta, which will be tau xy sin 2 theta. So if I simplify this, I would get this as sigma x plus sigma y by 2, that is from this to this and this. Then we have this sigma x, then there is a negative sign here, so minus sigma y and divided by 2, this is plus, into we have this common which is cos 2 theta plus this would be tau xy sin 2 theta. Now this is the equation that we would be referring to as the normal equation for any plane which is inclined at an angle of theta with respect to vertical. Please note this equation is valid for a plane or an axis which is inclined at an angle of theta with respect to the vertical, as I have explained earlier. So that is what is indicated in this PPT, okay, tau sigma x. How we have got that I just now explained, so we have that equation here. Similarly, if we take this equation sigma f y dash equals 0, we have this, and using the trigonometric relationship as I have explained here and reducing that, we would get an equation for tau x dash y dash which is indicated in here, okay, which is equal to minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. These are the equations that we are going to use. This is for the normal stress along a plane and this is the shearing stress along a plane. Now the plane which is normal to the plane that we have considered this as the plane, okay. Now and we get sigma x dash in this. Now if we consider a plane along x itself, the normal stress that is going to be acting would be along y. So to obtain that which is given in this equation, the angle from here, this equation sigma f dash equals 0, this equation, we have to substitute theta in place of theta. If we substitute theta plus 90, because this axis, okay, when I take this one, this would be inclined at theta plus 90 degrees. So if I replace that, I am going to get the normal stress equation along y axis which is indicated in here in this equation. This is the equation that we get for sigma y dash. I hope all of you have understood this, right. Next we will see how we can solve problems on this. Note down the earlier PPT, if you look at it, this is the element that we have taken and the angle that we have measured is with respect to the vertical, okay. So this is angle theta and sigma x is positive because it is tensile, sigma y is also positive, and tau xy, look at the sense of tau xy we have taken. These are the positive axis or the positive sign that we have taken. Now to obtain the stresses along a plane, let us look at this problem. Now I will read this problem for you. For the given state of stress, determine the normal and shearing forces, shearing stresses exerted on the oblique face of the shaded triangle element shown. Use a method of analysis based on the equilibrium of that element as was done in the derivation. The derivation is what we have just now looked upon. Now using whatever I have explained for deriving that, the same concept is to be used to get the normal stress on this plane which is inclined at 75 degrees to the normal, okay. Now this diagrams is what is written, okay, as per what is being given to us. So we have taken only this triangular portion, okay. We need to find out what is the normal stress along this plane, that is sigma, indicated as sigma, and this is indicated as tau, which is the shearing stress, okay. Now the stresses that is going to be acting is the 45 megapascal, which is, now look at this, the sense of it, it is acting as a compressive stress, whereas this is 27 megapascal is acting as tensile stress, then the shearing stresses, okay, which is acting. So we have taken this plane. Now to find out the areas of this diagram is given. The area taken here, this is A. So this angle is inclined at 75 degrees with the vertical, whereas with respect to horizontal it would be 90 minus 75. 90 minus 75. 90 minus 75 would be 15 degrees, which is given here in this one. So, if this is the area A, then the area, horizontal area would be A cos 15 degrees and the vertical area would be A sin 15 degrees, as I have explained earlier also. Now, with this, what are the forces? Now, these are the stresses that is acting on these planes. This is the areas. So, this gives the force diagram. Okay. So, we multiply the stress into the corresponding area, we get the forces that is going to be acting, which is indicated here in this diagram. So, let us take one by one. So, this normal stress is indicated as sigma. We multiply this with the area to get the force that is acting, the normal force, that is sigma A. Similarly, the shearing force tau is acting here. So, we multiply with the area. So, we get this as tau A. Okay. I hope this is clear. Then let us take the forces acting on the horizontal plane. So, the shearing stress is 18 megapascal. So, that you multiply with this area, which is A cos 15. So, we get this as 18 into A cos 15. Then the compressive force that is acting on this plane is 45 megapascal, multiply with the area again. So, it becomes 45 A cos 15, which is indicated here. This is the force. So, let us take next the forces acting on this plane, the vertical plane or vertical axis. So, this is tensile force now, which is 27 megapascal, that we multiply with the corresponding area, which is A sin 15. So, we get this as 27 A sin 15 degrees. Similarly, the shearing stress, if we take, it is 18 megapascal, we multiply that with the area. So, we get it as 18 A sin 15 degrees. Now, these are the forces that is going to be acting on this triangular element that we have taken, which we got it from this stress, plane stress element. Now, let us find out what are the forces that is going to be acting normal to this plane, the inclined plane, which is inclined at an angle of 15 degrees with the horizontal. So, we will sum up algebraic sum of all the forces that is acting along this plane, which is given as sigma f is equal to 0. This is the positive sense that we have taken. This is the sense of this forces that is going to be acting. So, one is sigma A, which is acting, which is given here, sigma A. Then, if you take this 18 cos 15 degrees and resolve this parallel to this and perpendicular to it, first we will take parallel. So, when I resolve this along this axis, I get the sense to be same as this. So, it is positive. Then, when I resolve 18A cos 15 degrees into sin 15 degrees, what I get, which when I take this as the plane. Then, you take this, which is 45A cos 15 degrees. When I resolve this along this, okay, this angle would be theta and the sense would be same as this. So, again you can see that it is positive here, plus 45A cos 15 degrees is the force, into the component of it, the angle is this. So, we get it as cos 15. So, we have resolved these two along this axis. Now, let us take this. So, what we have is this force 27A sin 15 degrees. I need to resolve this along this axis. So, I get the sense to be acting away from the sense as indicated here, which would be along this. So, that would be negative minus 27A sin 15 degrees is the force. So, I have to multiply that with the sin 15 degrees, because when I resolve this, I get this as the angle 15 degrees. So, this would be the cos component. So, that is what is indicated here. Next, if I take this, I have to resolve this along this axis. So, when I resolve it, this sense would be same as this along this. So, it is going to be 18A sin 15 degrees into this is the angle that we are getting. So, it is into cos 15. The sense, both the sense are same. So, we get this to be positive. So, when I take this entire equation and equate it to 0, because algebraic sum of the forces has to be equal to 0. So, this, the areas everywhere you can see you have area every term. So, I can remove that and take this sigma on the other side. So, and sum of all this, I get it to be sigma equals minus 49.2 megapascal. This is what I get. Now, this I got it because I have solve this problem from the first principles, that is resolving all the stresses, first converting all the stresses into forces and then resolving all the forces along the normal axis and then getting the value. So, from this I get this equation. Now, we have derived the expression when we took sigma and tau as the general expression and solved it. So, using that equation, if we solve using this equation tau xy, or rather this equation for this problem, let us see whether we get the same answer or not. Now, for that I will use the blackboard. So, this is the normal equation that we have derived, which is on the board. So, we will use this equation and see whether we would get the same answer when we use the formula. But for this we may have to do some, we have to note down a few things and I will write that on the board. Now, the stress that we have is this, we have this as well as this, and then the plane that we are taking is this angle is 15 degrees. Okay. So, what do we have here is 27 megapascal. This is compressive, sorry about that, this is 45, this is also 45, this is 27. Then we have the stress which is acting like this, which is equal to 18 megapascal. This is also 18 MPa. Now, here the sigma x value, that is this one, is 27 megapascal. Then sigma y, this is tensile whereas this is compressive. So, I will take it as minus 45 megapascal, and then tau xy is minus 18 megapascal, because if you remember when we solved problem or when we derived this expression, we had taken tau xy positive when it was opposite to this. So, I have taken the sense as negative. Very important, what we did when we derived was we took this as the angle as theta. Now, here theta is equal to 75 degrees. Now, substituting these values here, let us see what we get. So, sigma x dash equals sigma x is 27, sigma y is minus 45. So, divided by 2 from this is what we get, plus sigma x is 27. We have a negative sign here, sigma y is also negative. So, this becomes positive, plus 45 divided by 2, this into cos 2 theta, theta in this case is 75. So, we have to multiply this with 75. So, we get this plus tau xy in this case is negative. So, minus 18 into sine 2, the angle theta is 75. So, this is what we have derived this equation. For this equation, for the given plane stress, we have found out what is sigma x, sigma y, sigma z and the angle theta. With the sign convention, we have got this as positive because it is tensile, we have taken this as negative because it is compressive, and tau xy is negative because when we derived we took the sense of tau xy in the opposite direction as indicated here. So, we have taken it as negative. So, substituting these values in this equation, we have got this. So, if I solve this, I am going to get this as minus 9, and this would be minus, when I multiply it is cos 150, I get it as minus 31.18, and this term would be minus 9. If I total all this, I would get this to be minus 49.18 megapascal. So, this is the normal stress that is going to be acting on this plane. Now, if you see this value, whatever I have got using the formula matches with the value that we have got it when we used from the first principles we have derived, so it is 49.2 megapascal, minus 49.2 megapascal, whereas we have got here as minus 49.18, which is the answer that you should get when you use the formula. What is important is please refer to what you have derived, because in many books, if you are referring to different books, the sign convention used would be different. So you have to be careful what is the sign convention that you are using to derive the expression. The same sign convention is to be used when you are solving the problems also. Okay. So what we have got here is the normal stress. Similarly, we can also find out what is the shearing stresses. Okay. So now let us find out what is tau. So we will now resolve all the forces in this, whatever is acting along this axis, that is the tau axis. So here tau into A area, so we get this force, and the positive sense we have taken it to be like this. So we get this to be tau A plus 18 A cos 15 degrees, which is this force, and if I resolve this along this plane, I should multiply with cos 15 again, and when I resolve this, this would have the same sense as this, so it is positive. Next, we will take this is 45 A cos 15 degrees. When I resolve this along this, I get the sense to be opposite of this. So when I resolve this force, I get this as the plane. When I resolve it, it would be this force would be opposite to that of the sense that we have taken. So we have to take it as minus 45 A cos 15 degrees into sin 15 when I resolve this along that. Okay. Next, we take this, that is 27 A sin 15 degrees. We are resolving along this one. So when I resolve it, I get the sense to be opposite. So it is negative minus 27 A sin 15 degrees into the angle that we are referring now is this. This is angle theta, which is 15 degrees. So you have to multiply it with cos 15 minus, if I take this 18 A sin 15 degrees and resolve it along this, I get this as the plane which is opposite to this. Again it has to be minus 18 A sin 15 degrees into sin 15 degrees, and you equate it to 0. So this is the equation that we get, the forces acting along this plane. So if you add all this and simplify it, the answer that we get is tau equals 2.41 megapascals. Now let us see whether we get this approach. What we have done is from the first principles. Let us see whether we get the same answer when we use the formula that we have derived earlier. So the formula that we have derived earlier for the shearing stress is what I am going to write here. So on the board, I will erase this. So we will keep that as it is, and I will erase this. So what we had derived earlier for the normal stress, tau equals minus sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. This is the equation that we have for the shearing stress. So let us substitute these values here and see whether we get the same answer or not. So when I substitute that, what do I get? I get it as minus sigma x is 27, it is positive, sigma y is negative, there is a negative sign here, so this becomes plus 45 divided by 2 into sin 2 theta is 75 plus tau xy we have it as negative, so minus 18 into cos 2 into 75. This is the equation that we get. So if I simplify this I will get it as minus 18 because of this. Then this one I would get it as plus 15.59. So if I total this would come up to 2.41 megapascals. Now this value is same as the value that is indicated here. Okay, when we did from the first principles, we got the value as 2 0.41 as the shearing stress, and while using the formula also we have got the same value. I hope this is clear to everybody. And so when you are using the formula, be careful of identifying what is the positive sense, whether you are taking the right stresses or not, you have to be careful. Okay. Next we will solve another problem which is similar to the previous one. Now here, okay, I will make it fast because we are running short of time. So here if you observe, the forces that is given is, this is 60 megapascal which is compressive, and you do not have a force along this axis, whereas you have shearing stresses that is acting which is 90 megapascal. So converting this and taking the forces that is acting, it is indicated here, the areas are indicated in this diagram, then the forces are indicated in this diagram. So to find out the normal stress along this, the forces that is acting, everything is taken here, you add up everything from the first principles, you get the value as 32.9. Then you add up all the forces along this plane, okay, which you will get as sigma f equals 0, which you will get as this, the value would be this 71 megapascals. Now this we have got it when we did it from the first principles. In the same way, if you solve it by using the formulas, how it is going to be? Let us look at that. Okay, I will erase this. Okay, what do we have here is, this is what we have, the angle, this is 60 degrees, this force is 60 megapascals, and we have the shearing stresses as 90, this is also 90, and this is 60. Okay. So if you remember, when we derived the expressions, I had taken the plane like this with this as theta. So if I rotate this by 90 degrees in the clockwise direction, I will get similar one. So I am writing that now, this is 60, this would also be 60. Then we have this as the forces. So this is 90 megapascals. Now if I take that and take these values, let us see what we are going to get. So sigma x is negative minus 60 megapascals, sigma y for this case is 0. So tau xy is positive plus 90, and the angle that we have here, theta, when I resolve this angle, would be 30 degrees. So this theta is 30 degrees. So this is 30. So substituting this, I would explain for this the shearing stress. So I will erase this and see what we are going to get. So sigma x is negative, so it is minus 60, sigma y is 0, so 0. Then here theta is 30 degrees, so I will substitute this as 30 plus tau xy, we have got it as positive, which is 90, and cos 2 theta, again theta is 30 degrees. So if I solve this, the values that I am going to get would be, if I solve this, so I would get this as 25.98, and if I solve this, I get this to be plus 45. So the summation would be 70.98 megapascals. So if you observe this value and the value that we have got for the shearing stresses, when we used the general derivation 71, and here we have got it as 70.98. Now the normal stress, which is 32.91, I would leave it to the students to solve it by using the formula. I have given everything, just substitute the values in the formula and try to get this. Okay. Today whatever we have done is, from the basics we have a general two-dimensional force system. From that, how do we get the normal stresses acting on a plane which is inclined at an angle of theta with respect to vertical, is what we have looked at. Okay. So, in the next class we would look at some more problems if possible, and then we will see how to get principal stresses on a plane and what are the principal planes and principal stresses we are going to look at in the next class. I hope all of you have understood, or if you have any queries you can always contact me through VTU EduSat program or VTU online program, and then I would try to answer those questions. Thank you very much. Thank you.